we humans have known for thousands of years, just looking at our environment around us, that there are different substances, and these different substances tend to have different properties. And not only do they have different properties, one might reflect light in a certain way or not reflect light, or be a certain color, or have a certain at a certain temperature be liquid or a gas or be a solid. But we also start to observe how they react with each other in certain circumstances. And here's pictures of some of these substances. This right here is carbon, and this is in its graphite form. This right here is lead. This right here is gold. And all of the ones that I've drawn, that I've shown pictures of here, and I got them all from this website right over there, all of these are in their solid form, but we also know that it looks like there's certain types of air and certain types of air particles, and depending on what type of air particles you're looking at, whether it is carbon or oxygen or nitrogen, that seems to have different types of properties. Or there's other things that can be liquid, or even if you raise the temperature high enough on these things, you could, if you raise the temperature high enough on gold or lead, you could get a liquid. Or if you burn this carbon, you can get it to a gaseous state. You can release it into the atmosphere. You can break its structure. So these are things that we've all that humanity has observed for thousands of years. But it leads to a natural question that used to be a philosophical question, but now we can answer it a little bit better. And that question is if you keep breaking down this carbon into smaller and smaller chunks, is there some smallest chunk, some smallest unit of this stuff, of this substance, that still has the properties of carbon? And if you were to somehow break that down even further, somehow you would lose the properties of the carbon. And the answer is there is. And so just to get our terminology, we call these different substances, these pure substances that have these specific properties at certain temperatures and react in certain ways, we call them elements. We call them elements. Carbon is an element. Lead is an element. Gold is an element. You might say that water is an element, and in history, people have referred to water as an element, but now we know that water is made up of more basic elements. It's made of oxygen and of hydrogen. And all of our elements are listed here in the periodic table of elements. C stands for carbon. I'm just going through the ones that are very relevant to humanity, but over time you'll probably familiarize yourself with all of these. This is oxygen. This is nitrogen. This is silicon. This is Au is gold. This is lead. And that most basic unit of any of these elements is the atom. Is the atom. So if you were to keep digging in and keep taking smaller and smaller chunks of this, eventually you would get to a carbon atom. Do the same thing over here. Eventually you would get to a gold atom. You did the same thing over here. Eventually you would get this little small, for lack of a better word, particle that you would call a lead atom. And you wouldn't be able to break that down anymore and still call that lead, for it to still have the properties of lead. And just to give you an idea, and this is really something that I have trouble imagining, is that atoms are unbelievably small, really unimaginably small. So for example, carbon. My hair is also made out of carbon. In fact, most of me is made out of carbon. Most of all living things are made out of carbon. And so if you took my hair, and so my hair is carbon. My hair is mostly carbon. So if you took my hair right over here, and my hair isn't yellow, but it contrasts nicely with the black. My hair is black, but if I did that, you wouldn't be able to see it on the screen. But if you took my hair here, and I were to ask you, how many carbon atoms wide is my hair? What is So if you took a cross section of my hair, not the length, the width of my hair, and said, how many carbon atoms wide is that? And you might guess, Sal already told me they're very small. So maybe there's 1,000 carbon atoms there, or 10,000, or 100,000. I would say no. There are 1 million carbon atoms, or you could string 1 million carbon atoms across the width of the average human hair. And that's obviously an approximation. It's not exactly 1 million, but that gives you a sense of how small an atom is. Pluck a hair out of your head and just imagine putting a million things next to each other across the hair, not the length of the hair, the width of the hair. It's even hard to see the width of a hair, and there would be a million carbon atoms just going along it. Now, it would be pretty cool in and of itself that we do know that there is this most basic building block of carbon, this most basic building block of any element. But what's even neater is that those basic building blocks are related to each other. A carbon atom is made up of even more fundamental particles. A gold atom is made up of even more fundamental particles, and they're actually defined by the arrangement of those fundamental particles. And if you were to change the number of fundamental particles you have, you could change the properties of the element, how it would react, or you could even change the element itself. And just to understand it a little bit better, let's talk about those fundamental elements. So you have the proton. You have the proton. And the proton is actually the number of protons in the nucleus of an atom. And I'll talk about the nucleus in a second. That is what defines the element. So this is what defines an element. When you look at the periodic table right here, they're actually written in order of atomic number. And the atomic number is literally just the number of protons in the element. So by definition, hydrogen has 1 proton. Helium has 2 protons. Carbon has 6 protons. You cannot have carbon with 7 protons. If you did, it would be nitrogen. It would not be carbon anymore. Oxygen has 8 protons. If somehow you were to add another proton to there, it wouldn't be oxygen anymore. It would be fluorine. So it defines the element. It defines the element. And the atomic number, the number of protons, and remember, that's the number that's written right at the top here for each of these elements in the periodic table. The number of protons is equal to the atomic number. Is equal to the atomic number. And they put that number up here because that is the defining characteristic of an element. The other two constituents of an atom, I guess we could call it that way, are the electron, and the neutron. And the model you can start to build in your head, and this model, as we go through chemistry, we'll see it'll get a little bit more abstract and really hard to conceptualize. But one way to think about it is you have the protons and the neutrons that are at the center of the atom. They're the nucleus of the atom. So for example, carbon, we know, has 6 protons. So 1, 2, 3, 4, 5, 6. Carbon-12, which is a version of carbon, will also have 6 neutrons. You can have versions of carbon that have a different number of neutrons. So the neutrons can change, the electrons can change. You can still have the same element. The protons can't change. If you change the protons, you got a different element. So let me draw a carbon-12 nucleus. So 1, 2, 3, 4, 5, 6. So this right here is the nucleus of carbon-12. And sometimes it'll be written like this. And sometimes they'll actually write the number of protons as well. And the reason why we write it carbon-12, I counted out 6 neutrons, is that this is the total. You could view this as the total number of, one way to view it, and we'll get a little bit nuance in the future, is that this is the total number of protons and neutrons inside of its nucleus. And this carbon, by definition, has an atomic number of 6, but we can rewrite it here just so that we can remind ourselves. So at the center of a carbon atom, we have this nucleus. And carbon-12 will have 6 protons and 6 neutrons. Another version of carbon, carbon-14, will still have 6 protons, but then it would have 8 neutrons. So the number of neutrons can change. But this is carbon-12 right over here. And if carbon-12 is neutral, and I'll give a little nuance on this word in a second as well. If it is neutral, it'll also have 6 electrons. So let me draw those 6 electrons. 1, 2, 3, 4, 5, 6. And one way, and this is maybe the first order way of thinking about the relationship between the electrons and the nucleus, is that you can imagine the electrons are kind of moving around, buzzing around this nucleus. One model is you could kind of thinking of them as orbiting around the nucleus, but that's not quite right. They don't orbit the way that a planet, say, orbits around the sun. But that's a good starting point. Another way is they're kind of jumping around the nucleus, or they're buzzing around the nucleus. And that's just because reality just gets very strange at this level, and we'll actually have to go into quantum physics to really understand what the electron is doing. But a first mental model in your head is at the center of this atom, of this carbon-12 atom, you have this nucleus. you have this nucleus right over there, and these electrons are jumping around this nucleus. And the reason why these electrons don't just go off away from this nucleus, why they're kind of bound to this nucleus and they form part of this atom, is that protons have a positive charge, and electrons have a negative charge. And it's one of these properties of these fundamental particles. When you start thinking about, well, what is a charge fundamentally other than a label, and you start to get kind of deep. But the one thing that we know when we talk about electromagnetic force is that unlike charges attract each other. So the best way to think about it is protons and electrons, because they have different charges, they attract each other. Neutrons are neutral, so they're really just sitting here inside of the nucleus, and they do affect the properties on some level of some of these for some atoms of certain elements. But the reason why we have the electrons not just flying off on their own is because they are attracted. They are attracted towards the nucleus, and they also have an unbelievably high velocity. It's actually hard for, and we start touching once again on a very strange part of physics once we start talking about what an electron actually is doing. But it has enough, it's, I guess you could say it's jumping around enough that it doesn't want to just fall into the nucleus, I guess is one way of thinking about it. And so I mentioned carbon 12 right over here, defined by the number of protons. Oxygen would be not defined by having 8 protons. But once again, electrons can interact with other electrons, or they can be taken away by other atoms. And that actually forms a lot of our understanding of chemistry, is based on how many electrons an atom has or a certain element has, and how those electrons are configured, and how the electrons of other elements are configured, or maybe other atoms of that same element. We can start to predict how an atom of one element can react with another atom of that same element, or an atom of one element could how it could react, or how it could bond or not bond, or be attracted to or repel another atom of another element. So for example, and we'll learn a lot more about this in the future, it is possible for another atom someplace to swipe away an electron from a carbon. Just because, for whatever reason, and we'll talk about certain elements, certain neutral atoms of certain elements have a larger affinity for electrons than others. So maybe one of those swipes an electron away from a carbon, and then this carbon will be having less electrons than protons. So then it would have 5 electrons and 6 protons, and then it would have a net positive charge. So in this carbon 12, the first version I did, I had 6 protons, 6 electrons. The charge is canceled out. If I lose an electron, then I only have 5 of these, and then I would have a net positive charge. And we're going to talk a lot more about all of this throughout the chemistry playlist. But hopefully you have an appreciation that this is already starting to get really cool. Once we can already get to this really fundamental building block called the atom. And what's even neater is that this fundamental building block is built of even more fundamental building blocks. And these things can all be swapped around to change the properties of an atom, or to even go from an atom of one element to an atom of another element.